So we're going to graph y equals e to the x so that we can begin section 5.4, and eventually we will be differentiating and integrating exponential functions and talking about those applications. So I first want us to graph y equals e to the x, which is here under the second natural log, and we're just going to do a standard zoom of 6. Is that okay, you guys?
Yeah.
Okay. So here's e to the x, and it's like Morgan said, see that horizontal asymptote right down here? Yeah? You can see how like it's kind of hard to see, but you can see how it's approaching 0 but never actually gets there. Okay. I also want you to go to y equals and put in a second function. Put in y equals natural log of x in the second function. Well, and mine won't graph for some reason.
Can you pause it? You had to press enter again.
I what?
You see it's paused over there when the little dots are moving around?
I know.
You gotta hit enter.
You think it'll work?
Yeah.
You're so smart. Thank you. Okay, so we go to y equals. We're going to type in ln of x. And I want you guys to compare those graphs and tell me what's true about them. How do you know they're inverses? Just by looking at it. That is true. They are inverses. But how do you know?
They're reflections.
They are reflections about
The origin.
not almost the line
The line of
x equals y or y equals x is the line of symmetry. Yeah, I'm serious. If you take this graph and you fold it right here along y equals x, you can see that they would match up perfectly. That's how you know that two graphs are inverses, okay? All right, so that's what we need to know to get us started. Just to kind of keep that in the back of our minds. That y equals e to the x and y equals ln of x are inverses of each other. I want us to talk about solving these exponential and logarithmic equations. Just as a recap from what we did back in the pre-cal portion. Remember that unit we did that you all loved so much? Way early on. I look back at those tests, and you guys struggled with this, so let's see if you're still going to struggle. 92 is awesome. Okay. So, if we have 7 equals e to the x plus 1, and we want to solve that for x, how do we solve an exponential equation? Take the natural log of both sides, but you have to make sure that the e is isolated first. Like if that were a 5e to the x plus 1, you would need to divide by 5 first. So we're going to take the natural log of both sides. And because these guys are inverse operations of each other, these will undo each other and go to 1. And so we're just left with the natural log of 7 equals what?
X plus 1.
X plus 1, perfect. So if I want to know what x equals, I just subtract 1 from both sides. And that's going to equal my x. And for the sake of calculus, we'll leave it exact, but as we saw with our bell ringer, if we want to kind of know what the meaning of that is, we actually find the value. Because that really number has no major significance to us. So now give me the approximation. What's the natural log of 7 minus 1?
0.946.
Really? Yeah, I guess that's right. E is 2 something. Point what?
946.
0.946. Okay, so you can have it both ways. Exact, approximate. And that's how we solve exponential equations. Let's go the other way now and let's solve a logarithmic equation. We have that the natural log of 2x minus 3 is equal to 5. Let's pause for a second, let everybody get caught up. So if we have the natural log of 2x minus 3 equals 5, and we want to solve it, what do? How do you solve a logarithmic equation? You loop it. You loop the log. You take the base, which is an understood what? E. An understood E. And we say that we rewrite it in exponential form, also known as looping the log. And we say e to the 5th is equal to 2x minus 3.
There you go.
There you go. So we add 3 to both sides. And so 2x is equal to what? E to the 5 plus 3. And so 1x is equal to?
E to the 5 plus 3 all over.
E to the 5 plus 3 all over 2. That would be your exact answer. Give it to me as an approximate answer.
Oh my god.
Oh, goodness. Type it in for me, Connor. Tell me what you get.
Alright, so I'm gonna go with this term next.
E to the 5 plus 3 all over 2.
75.
I'll choose the filler.
0.70.
75.17-ish.
Or 7.
Yeah, 75.71.
How about just 75.7? How does that sound? Good enough? Okay, that's our approximate answer. So that's just basic algebra there. How to solve exponential and logarithmic equations. Now we want to talk about the derivatives of exponential equations. And why would we care about the derivative of an exponential equation?
Calculus.
No, well, let's pretend we do. Why would we care? Okay, like if we cared, why would we care?
The derivative would tell us the slope at any given
point, and the slope would tell us the rate of change of our independent variable with respect to our. Okay, got it. You were so good. You're good at filling the blank. Okay. So, and fortunately for you. Oh, time out. Do you guys remember these properties? Apparently they're going to be important later.
No.
That if you have e to the a times e to the b, that when you multiply, what do you do to your powers?
Add.
You add. And if you have e to the a over e to the b,
Oh, it's kind of like
Okay, I
the log, it's like
remember
the
those
log,
powers.
the natural logs or whatever, except this is just applying the exponents.
right, in reverse. Because natural logs are just another way of writing exponents. And we've already reviewed those properties, right? Yeah. Okay. All right. So, because we may at some point care about finding the rate of change or the slope of an exponential function, we need to know how to take the derivative of a natural exponential function. And the derivative with respect to x of e to the x is e to the x. That's the simplest derivative you will ever get in your whole entire life. What's the derivative of 2x?
2.
What's the derivative of x squared?
2x.
2x, right? What's the derivative of x squared plus 5x?
2x plus 5.
You're using the power rule to do that, right?
Yeah.
Yeah. To take the derivative of an exponential function, you don't do anything. It is its own derivative. And I know this is not going to amaze you, but it is going to amaze me, so I'm going to say it anyway. Because it is its own derivative, the slope at every point on the graph of y equals e to the x is exactly the same as its y value at that point. Isn't that cool? Yeah, its slope is always equal to its y value.
So like 3, 3, 4, 4.
Yeah, so like if you had e to the second, like if I said e to the x and I put in 2 for x, then the slope is e squared, which means it's the same as its y value. So it's the simplest derivative you could ever get. If, however, you don't have just an x as your exponent, if you have something else, we'll call it u. If you are trying to take the derivative of e to the u, all you do is you keep the original, and then you multiply by the derivative of the exponent. So I'll give you a minute to digest that. So to take the derivative of any exponential function, you keep the original and multiply it by the derivative of the exponent. You can't see that in this one, because what is the derivative of the exponent? 1. But if there's something other than an x there, you have to use this little piece here, which is just a variation of the chain rule. Okay, so here's what we got. We started with y equals e to the 2x minus 5 and ended with y prime equals
2e. No, e times 2.
we kept the original, we multiplied by the derivative of the exponent, we rearranged it to what, Kaylee?
2e to the 2x minus 5.
Perfect. So there's no trick, no gimmick, that really is just the answer. Let's try another. F of x equals e to the negative 3 over x. So as those exponents get more complicated, so does the calculus involved.
I love it.
So the first thing I'm going to do is I'm going to rewrite that exponent in a format that I can easily see its derivative, okay? So if I have e to the negative 3 over x, that's the same as e to the negative 3x
To the negative 1.
perfect. And if you look at it that way, it's much easier for you to take that derivative using the power.
Negative 3 for L.
Oh, you use the power rule.
So f prime is equal to the original, which is e to the negative 3 over x, times the derivative of the exponent, which is this guy right here.
3x.
Which I
No, we had no natural log.
Right. Now guys, be careful, we're not integrating. We're going back to derivatives, all the way back to chapter 6.
No, it'd be 3x times 3 over x.
Okay, we're all saying basically the same thing, except for one of us is trying to bring a natural log into this. So I don't know who we are, but we're gonna fix it, okay? If I asked you to take the integral of that exponent, it would be negative 3 natural log of absolute value of x. But we're not integrating, we're taking the derivative. And the power rule for derivatives says that you take the power times the coefficient down 1 on the power. So that would be negative 1 times negative 3, which is x to the negative 2. And Andy, you already had it cleaned up for us. What was it? That's the same as
3 over x squared to e onto the negative 3 over x.
right. So you're not allowed to leave negative exponents except on an e. They will let you leave them on an e, but not on a variable. So this piece does need to be cleaned up right here and brought down to this. And then we'll multiply them, 3e to the negative 3 over x, all over x squared. That is perfect. Couldn't ask for better.